Now we define the message from a factor node of fs to the random variable node of xi as mu si bracket xi, and this is defined by the equation shown here. One important thing to note is that since we are passing a message from a factor node into a random variable node, since we are passing the message from a factor node into a random variable node of xi over here, what this means is that the factor nodes here would consist of the random variables of all the neighboring random variable nodes of, for example, xi, xj, and xk over here. In this case, in this example here, it could consist of xi, and as well as we can say that this is consists of all the random variable we will collectively call xj and xk over here as all the random variables in the neighborhood of s excluding I itself. Since we are passing the message from the factor node of fs into the random variable node of xi over here, it better not consist of all the other random variable except for this random variable I itself. So what this means is that we would have to marginalize away all the random variable that is contained in the factor node of fs except for the random variable of xi itself, and over all the potentials, all the factors that is represented by fs, as well as the messages that comes into fs. In this example here, it would be xj, the message from xj, as well as the message from xk over here, which contains j and k respectively in these two messages. So in order for the message that passes from fs to xi over here to consist of only xi, we would have to marginalize over all the other random variables except for I itself that is connected to the factor node of fs. So we'll further define the message from a leaf random variable nodes to a factor node as 1, since in this case here we have seen earlier that in this case here the factor would directly be a function of xi. So here over here there isn't a need to do anything when we are passing a message from a leaf node of random variable xi to a factor node of fs. And when we are passing a message from a leaf factor node to a random variable node as shown in this figure over here, then we will directly write the message as the factor itself. There's no need to do any form of marginalization, since this particular factor node here would only consist of xi in this case over here. And it does not consist of any other random variable from its neighbor, because it only has one neighbor, which is xi itself. There is also a similar message passing protocol in a sum product algorithm on a factor graph. So here a node can only pass message to the neighboring nodes when and only when it has received all messages from all its other neighbors. So this is the same message passing protocol as the sum product algorithm that we have seen for undirected graphical model or a directed graphical model. Now suppose that we define the root node in the factor graph as the random variable node of xi. We'll only be able to compute the marginal probability distribution after xi has received all the messages from its neighboring factor nodes as defined from the message passing protocol. And similarly, the downward message passing from the random variable node or the root node of xi would only begin when we have received all the other messages from all the other factor nodes that is linked to the random variable node of xi. Here's the pseudocode for the sum product algorithm on a factor tree. Similarly to the sum product algorithm that we have seen in the past lecture, that we need to first form the evidence potentials. So we'll add all the evidence potentials as defined by the marginalization trick that we have seen in the earlier lecture. So after we have added all the evidence potentials, We'll begin by recursively collecting messages from the leaf nodes to the root of the factor tree. For a factor node of fs, for example, we'll do this by first collecting all the messages from all the random variables that is of one hierarchy level lower than fs. So in this case, we'll collect the random variable node to the factor node message, which we denote as mu of j of s. Suppose that this is the random variable nodes of xj, and we'll collect all the messages upwards from the one hierarchy level lower than fs towards fs, denoted by this equation over here. And this would be a product of all the messages from the random variable j towards fs. And note that xj here is one hierarchy level lower than fs in the factor tree that we have defined. So for each one of these random variable nodes of xj, this will in turn be collecting all the messages from the factor nodes that is one hierarchy level lower than xj, which we denote as ft here, for example, where t here is defined to be all the other nearest neighbor to xj except for fj itself. And this would consist of all the product terms of the factors defined by this equation. So once we are done with collecting all the messages towards fs, we'll send a message from fs towards the random variable which we denote as xi over here in a hierarchy level above fs, and this would be denoted by mu, the message of mu over here. And since we are sending a message from a factor node which is denoted by fs over here towards a random variable node denoted by xi over here, so this particular message over here, it better not contain any other random variable that is linked to the factor node of fs over here. And what this means is that we have to marginalize away all the other random variables except for xi itself, and hence there's a summation, and this will be a summation over the multiplication of all the messages that comes into fs as we have computed in the earlier stage, multiplied by the factor represented by this factor node of fs itself. And once we are done with the upward propagation of the messages towards the root, we'll do a downward pass of the downward propagation from the root node towards the leaf node. Now suppose that we have the root node as xi, a random variable node of xi over here. We'll pass the message downwards towards the factor node of fs, and this is denoted by the message of a random variable towards the factor node denoted by vis over here. This is what we have seen earlier, bracket xi. And since this is a downward pass, what this means is that we better be taking into account all the other factor nodes, the upward message that is given by other factor nodes, which we denote by mu t of I over here. Suppose that this is a factor of ft, and hence this message over here would be given by this equation over here, which simply says that it's a product of all the upward messages or the messages from the factor node of ft towards the random variable node of xi, where t here is in the neighborhood of xi except for s itself. And once we are done with the propagation of the messages from xi to fs, we'll do a downward propagation. We'll further distribute the message from fs towards the other random variable nodes that is connected to fs in a hierarchical level lower than fs. Now suppose that we denote this particular random variable here as xj, then this particular message over here would be mu of s towards j. And since we are propagating a message from a factor node towards a random variable node of xj, then this message here, it better contains only the random variable of xj with all the other random variables that is in the factor eliminated or marginalized away. And this is given by this equation where we say that we have a factor node of fs, and this is linked to a random variable nodes of xj, or in this case here the notation is I, where xi here is one level lower than fs. So we are distributing the message downwards. So this would be a mu si xi, and since it contains only xi, we better eliminate away or marginalize away any random variable nodes that are which we call xj, that is in connected to this factor node of fs. Hence the marginalization over all the neighbors except for the random variable of I. And in this case over here, it would be a product of over the product of all the messages that are coming from the random variable of xj into f of s from a hierarchy level that is above fs and the factor of fs itself. So all this contains of all the other random variables together with the random variable of xi. And what we are interested in this message over here would be the one that is only containing xi. Hence we need to marginalize away all the other random variables that is connected to fs except for I itself. And once we are done with this downward distribution, we have computed all the messages in the factor tree, and we can make use of all these messages to compute the marginal probability of any random variable in the factor graph. An example would be a 3 random variable undirected graphical model, which is a chain undirected graphical model shown in this figure here. So the conditional probability of x conditional upon x evidence, which means that we could observe some of the random variables in this case over here. So we've seen this notation in the previous lecture, and this is given by this potential function, where ze over here is the partition function taking into account the evidences, and it consists of the unary and as well as the binary potentials. So we can directly convert this undirected graphical model into a factor graph where we simply let the unary potentials be each one of these factors fa, fb, and fc respectively, as well as the binary potentials are represented as the factors that is connecting each pair of random variable in this factor graph, denoted as fd and fe. And we can see that here's an example of the message passing algorithm or the sum product algorithm on this factor tree. So as following the pseudocode that of the sum product algorithm that we have seen earlier, we start the message passing from the leaf nodes, which in this case over here would be the factor node. And since this is the leaf nodes are the factor nodes, we'll not do anything but simply propagate the factors into the next level of the random variable nodes over here. So in this case here, we will have mu a1, which is simply the potential represented by fa, as well as mu b2, which is the potential represented by fb, and fc for mu c of 3, which is the message from the factor nodes here into the random variable nodes of x3. And once we are done with this, we will collect all the messages from x1 and x3 respectively. So since there's only one neighbor other than the next factor node in the higher level, we will directly write this as the v1d, the message from the random variable of x1 towards the factor nodes of fd as v1d, and this would be directly equal to mu of a1, which is the message that we pass from fa towards x1. Since there's no other factors except for fa that is one level below the random variable nodes of x1 in the factor tree. And similarly for x3, we're propagating a message from x3, the random variable node of x3, into a factor node of fe. And in this case, the message would be denoted by v of 3e, which consists of only x3. And since there's no other factor node that is one level below x3 except for fc itself, the message of v3e would be simply equals to the message that we propagate upwards from fc towards x3, which is mu c3. Next, we'll continue the message passing upward to the root node of x2, and we can see that this message is from a factor node of fd into the random variable node of x2. And in this case here, as defined in the message passing protocol, that since this is a message that is passed from a factor into a random variable node of x2, then this message better only contains x2, and therefore we need to marginalize away any other random variables that is contained in fd over here. And in this case, that would be over x1 as defined by this message passing protocol that we have defined earlier on here. And now in this case here, we can see that this message would consist of this marginalization over here. It would be over the potential that is in the factor, which is the potential of over x1 and x2, multiplied by the message that we have computed earlier from the random variable node to the factor node of fd, which is given by mu of a1x1. And this has to be done over a marginalization of x1. Similarly, we can see that the message that we propagate from the factor node of fe over here, which we define to be mu e2, because this is a message from fe to x2, it better consists of only the random variable of x2. And this means that we would have to marginalize away all the other random variables that is contained in these factors, and this would be a multiplication over the factor of fe defined by the potential over x2 and x3, multiplied by the message that we have computed earlier from the random variable of x3 to fe, which is defined by mu of c3 over here at x3. So we have to do this, we have to marginalize the product of these two terms over x3, and this would be the message that we pass from the factor nodes of fe into the random variable node of x2. And once we have all the messages into the root node of x2, we'll start the downward passing, or we'll start the distribution of the messages down from the root node to all the leaf nodes. So here we can see that the first three messages that we need to pass would be from the random variable to a factor node over here, which we define as v of 2d, v of 2b, and as well as v of 2e. So one important thing to note here is that suppose that we are looking at this message over here, which we pass from x2 towards the random towards the factor node of fd. In this case over here, since this is the root node, what it means is that we can only start passing of this message after we have collected all the messages from the factor nodes into the root node, following the message passing protocol. And what is also needed over here would be this particular message. It needs to contain the other messages, the other two messages that we pass in from the factor nodes of fe as well as fb into x2. So these two nodes, these two messages here are important in this case here. And we can see that this message from the random variable x2 to fd, the factor nodes of fd, would be defined by simply the product of all the messages, the factor to random variable messages that we have that is in the neighborhood of x2 except for fd itself. And this would be simply given by the in this case here, the message of v2b x2 will be simply given by the multiplication of the two messages from fb and fe respectively into x2. So we can verify that this is also true for the other two messages that we pass from x2 to the other two factor nodes over here. And once we are done with this, these three messages over here, we can also start to propagate the message, distribute the message further down the tree. And in this case here, we saw that we can see that there are two other messages, mu of d1 and mu of e3 over here, which we can compute using the same method. In this case here is a factor to variable. So what it means is that we better marginalize away all the unwanted random variables except for the random variable that we are passing the message into. So in this case here, mu d1, we are passing the message into x1. What it means is here is that since this is also connected to x2, we need to marginalize away x2 over all the messages, or the potential or the factor that is represented by fd multiplied by the message that we are passing in from x2 to fd, which is mu, which is v of 2d x2 over here. So we can see that indeed this is the case over here, and you should verify for yourself that this is also true for the next message that we pass from e to 3. And once we are done over here, we will follow the same protocol to further distribute the message down to the leaf nodes, which happens to be a factor node. So what's interesting here is that although we have looked at the message passing algorithm or the sum product algorithm on a factor tree, it turns out that the sum product algorithm on a factor tree is exactly the same as the sum product algorithm on an undirected graphical model or a tree-like undirected graphical model. Now let's prove that this relation is true. Let's look at the message that is passed from a random variable node of j into a random variable node of xi in an undirected graphical model. So what this means is that I have a random variable node of xj, and I also have a random variable node of xi over here, and these two are connected to each other. So what I'm doing here is that I'm computing the message from xj into xi, which I denote as n of ji xi. And since I'm passing a message from the random variable of xj into the random variable of xi, what this means is that I better marginalize away the random variable of xj in the final message. And I will do this marginalization over the unary potential of xj, or the evidence potential of xj, as well as the binary potential of that is denoted by this edge over here, which is over xi and xj, and multiplied by all the messages that are coming into xj, into this random variable node of xj. So what this means is that there could be other nodes that are linked to xj over here, which I generally denote as xk, where k is defined to be all the other random variables linked to xj except for xi itself. And all these messages that are coming in to from k towards j, which contains of xj only, I will take them into account over here, and I will marginalize over the product of all these terms, and this will form the message that I pass from xj into xi. So we'll see that the message that is passed from the random variable node of xj into the random variable node of xi in an undirected graphical model is equivalent in a message passing in the factor graph, that we denote these two random variables as again xi and xj, but in the factor graph these two nodes would be linked together by a factor which we call fj. So we'll see that this mji over here is equivalent to the message that is being passed from fs into xi over here, which we denote as mu of si xi in this case over here. And following the definition of the message passing, or the message that is passed from a factor node into a random variable node of xi, this is given by, because we are passing the message from a factor to a random variable, this means that we better marginalize away all the other random variables that is contained in this factor. And in this case, it would be all the random variables that is connected to fs except for the random variable of xi itself. And we'll marginalize this over the factor of fs, which consists of all the other random variables in its neighborhood, multiplied by all the messages that are coming into the factor node of fs from other random variable of which we generally call xj, where j here is in the neighborhood of fs except for the random variable of I itself. Since we are saying that the factor graph that we are representing here should be the same as the two-node undirected graphical model that we have seen earlier on here in this undirected graphical model proof, this means that the neighborhood of fs except for I itself should only contain the random variable of xj. Hence, we can rewrite this term over here into the summation over xj, and all the neighborhood of s would only be xi and xj itself. So again, the message that is passed towards fs would only be from xj itself, except for the random variable of xi. So in this case, we can rewrite this message over here as v of js, which contains the random variable of j itself, and in this particular equation, which we can further evaluate into the message that is collected from xj by propagating all the messages into xj from all the other factors that is linked to xj except for fs itself, which we call generally of ft here, where t is in the neighborhood of xj except for fs itself. And we can see that now we can rewrite this term here, the binary potential here, to include the evidence potential of xj, which we denote as xj and a superscript of e, and as well as the binary potential. And t here would be simply defined as the same message that we have seen earlier, but n prime is defined over n prime, where n prime here denotes the neighborhood of xj, omitting the singleton factor associated with the evidence potential. And now we can see that the two terms here, they are equivalent to each other, which means that the message passing step in a factor graph is the same as the message passing step in an undirected graph, or a directed graph which has been converted into an undirected graph through the step of moralization.